So we have this compound C3H8O. C3H8O. So the first structure there is showing us that it's an alkanol. Tells us it's an alkanol with the structure COH, and then we have H. Don't be confused with the way they wrote it. Don't be confused. It is still the same thing. And the second is C, and we have OH up there, and we have OH there, H here, H, and H. Now, let's look at the last compound. The last compound there is COC. Then we have H here, H there, H over here. And we have H here, H there, and then H and H. So we can see they all have 3 carbon atoms, 8 hydrogen atoms, and 1 oxygen atom. So this is an example of functional isomers. Looking at this has OH, compound 1, compound 2, and compound 3. They all have the same molecular formula. But compound 1 has OH, and OH tells us that it is an alkanol family. Compound 2 also has OH attached together. It tells us also that it is an alkanol family. But compound 3 is not having its own structure as OH. It is having it as ROR. And when you recall, when we are talking about functional groups from the beginning of the class, homologous series that has this formula ROR are called ethers. This is the homologous series called ether. It is not an alkanol. So you can see this is ROR, and it is actually belonging to the homologous series called ether. So this is an example of a functional isomer or functional isomerism. So when 2 or more compounds belong to different homologous series and have different functional groups, but though they may have the same molecular formula, they are referred to as functional isomers. So, having seen that, I believe that is clear. I believe that is very clear. Let us take a look at another example of functional isomers. Let me give you this so that you get to understand what we mean by functional isomers better. Let us look at this. We may have compounds like this. This is not benzene. That is not benzene. And then we have this. We have that. Okay. We have something like this. So, looking at what we have on the screen displayed, do they have the same molecular formula? That is the question. Do they have the same molecular formula? Let us take a look at what we have and try to understand. Now, the first structure 1, and the second one 2, compound 2. Compound 1 has carbon at each of these junctions, carbon, carbon. And since they all have carbon, carbon at each of these junctions, it means that there are 6 carbons there. And to satisfy the bonding rule, each of these 6 carbons are already bonded to themselves and they have 2 bonds. So if I take this first carbon here, if I take this to be 1, 2, 3, 4, 5, and 6. Carbon 1 is bonded to carbon 2 and carbon 6. Carbon 2 also binds to carbon 3 and carbon 1. Carbon 3 is having bonding with carbon 4 and carbon 2. Carbon 4 is having bonding with carbon 3 and carbon 5. Just that way, carbon 5 binds with carbon 6 and carbon 4. So they all have 2 bonds each. What it therefore implies that they need 2 more bonds. So that is why hydrogen comes in. Hydrogen comes in for each of them. So each of them will bind to 2 hydrogens, to 2 more hydrogens. So if each of them is giving 2 hydrogens, so what it literally means is that this compound is 6,6H12. That's what it means, 6,6H12. There are 6 carbon atoms and 12 hydrogen atoms. Now let's look at compound 2. Compound 2 is having carbon, 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 carbon in each of those places. So we also have 6 carbon atoms. Now since there are 6 carbon atoms there, how many hydrogens will each of these 6 carbon atoms have? How many hydrogens? Let us take a look at it. We have seen this before when we were doing our IUPAC nomenclature, and I told you whenever you come across compounds like this, you don't need to fidget, you don't need to panic. It is just the same thing as you know. So this is carbon having double bond to another carbon, and that is having a single bond to another carbon, and this is having single bond to this. This is to this, and single bond to that. So this is just what it simply is. That is how it looks like. That's what we call seesaw structure. So each of them must have 4 bonds. So it means this automatically has hydrogen even though it's not visible. This will have 2 hydrogens even though it's not visible. When you see a structure like this, the hydrogen is already there, but needless to write it. It is not usually written, but it is presumed that it is there. Just like we can have 1x in mathematics. We don't need to put 1, we just have to put x. So we know that 1 is there, but we don't necessarily need to write it. So that is how the seesaw structure for organic compounds is. So we know that the hydrogens are there, but we don't need to put them unless we just need to explain, just as we are doing now. So this carbon at the extreme right must have 3 hydrogens to complete the 4 bonds. The one following it have 2. The next have 2. The next also is going to have 2. And let's look at the 2 carbon atoms at the left-hand side. The 2 carbon atoms at the left-hand side. This carbon atom, if I am to number them this way, let's number them beginning from 1, 2, 3, 4, 5, and 6. Let's just number them that way for easy identification. Now, it is clear that carbon 3, 4, 5, 6 have been given hydrogen atoms that will complete their bond. So let's look at carbon 1 and 2. Carbon 2 is bonded to carbon 1 and carbon 3. It has 1 bond with carbon 3, and it has 2 bonds with carbon 1. So automatically what carbon 2 needs is 1 more hydrogen. Can you see that? Now let's look at carbon 1. Carbon 1 is only having 2 bonds with carbon 2. So it means it's going to need 2 more bonds with hydrogen. So that is carbon 1's bond. So every of this carbon in this chain is complete. Now let's count how many hydrogens. we have beginning from carbon 1. Carbon 1 has 2 hydrogens. Carbon 2 has 1 hydrogen, that's 3. Carbon 3 has 2, that is 5. Carbon 4 has 2, that is 7. Carbon 5 has 2, that is 9. And carbon 6 has 3. 9 plus 3 gives us 12. So it means this compound has 6 carbons and 12 hydrogens, just like compound 1. So we can see that they both have 6 carbons, 12 hydrogens, but their structure is not the same. Compound 1 belongs to the homologous family called cycloalkanes. Cycloalkanes. They are cyclo compounds. They are not really aromatic, but they are cyclo compounds. While the second compound, compound 2, is in the alkene family. It belongs to an alkene. It is an alkene compound. So this is actually what we should get to understand. So when 2 or more compounds belong to different homologous series, having different functional groups, but they have the same molecular formula, then such compounds are said to be functional isomers. Functional isomers. So it is as simple as that. Let us take a look at a last example on that. We have these 2 compounds, compound A and compound B. Compound A and compound B, they both have this formula C2H6O. That is to say they have 2 carbons, 6 hydrogens and 1 oxygen in their structure. And for compound A looks like this: carbon, carbon, OH, hydrogen, 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 hydrogen. Now, I don't know what compound A is, and I don't know the homologous family it belongs to, but we shall get to see that. Now, for compound B has the structure CCH. We have COC H. This is compound B. This is compound B. So let us look at what compound B is and what compound A is. They both have 2 carbon atoms, 6 hydrogen atoms, and 1 oxygen. That is actually what they have. 2 carbon atoms, 6 hydrogen atoms, and 1 oxygen. So, looking at compound A, it has 2 carbon atoms are there, yes. 6 hydrogen atoms are there, yes. 1 oxygen atom is there. Yes, it's correct. Compound B also has the same thing. 6 hydrogen, 2 carbon, 1 oxygen. But looking at their structure, it is not the same. And if we are to consider their functional groups, we'll observe that in as much as A has 6 hydrogen atoms, one of the hydrogen atoms is not really independent. Instead, it is in combination with oxygen, and that makes it an alkanol, OH. It makes it an alkanol. But in the case of compound B, all the hydrogens are independent. The oxygen also is independent. So it is not like compound A, whose one of its hydrogen is not independent, is attached directly to OH, and that makes it an alkanol. So it means that this is an alkanol. What kind of alkanol? It is what? Ethanol, because it has 2 carbon atoms. This is ethanol. So it is an alkanol family. It has a different functional group, which is OH. But in the case of compound B, this is what we call dimethyl ether. Dimethyl ether. Dimethyl ether. Dimethyl ether. Because there are 2 methyl groups. 2 methyl, 1 methyl and another methyl. And this is ROR. This is also another, this is ether, ROR. And it is called dimethyl ether. So we can see that compound B belongs to ether homologous series, and compound A belongs to the alkanol homologous series. And they both have different functional groups. but they only share the same molecular formula. So this is what we refer to as functional isomers. So before we look at the other types of isomers, I now want to challenge you, dear students, with the following questions. Kindly put yourself to the test by answering these questions. How many more isomers can be formed from the compound below? You are given a compound and the name of the compound is given to you. And then we have that if you give the name of these isomers, you are to also tell us what homologous family do they belong to. That is to say, the isomers that you formed, what homologous family do you think it belongs to? So that is your STS for today's lesson. As our first STS, we are going to see other questions as we proceed. So having seen that, do kindly answer the question, and you can send it across to us through our platform, and we shall adequately attend to your questions and answers. Okay, so let's proceed to the other types of isomers.